Hello grade 9s. Okay, so we're a couple of lessons into factorizing. I hope you're really enjoying it. I really love factorizing. It's such fun. So what have we done so far? We've done our first topic of factorizing, which was the highest common factor, which could be a highest common bracket, and you also have to be mindful of the switcheroo, which we've just done in our previous lesson. And so now we're on to the second type of factorizing. So when we factorize, the order in which I'm teaching you is the order in which you check when you're asked to factorize a question. So if the question says factorize, the first thing you do is you check for a highest common factor, because if there is a highest common factor, you must first take it out. The second thing you do is you check for today's topic, which is called a DOTS. Now that's an acronym, so what does it stand for? DOTS stands for difference of, the O stands for of, so of, T stands for 2, and S stands for squares. So dots is just a shorthand way of saying difference of 2 squares. Okay, now I'll explain to you what that is at the moment, but perhaps write the heading, push pause on the video and write down that note, that dot stands for difference of 2 squares. Now let's understand each of these words. What does the word difference mean in maths? In maths, difference means subtraction. So if I say to you, what's the difference between 10 and 7? The answer is 3, because it's 10 minus 7. So you have to be looking for a minus sign when you're looking for a difference of 2 squares. If there isn't a minus sign or a subtraction sign, we have a problem. Okay, 2, I know you all know what 2 means, but this is a very, very good hint for whether a question is a dots or not. You have to have 2 terms in order to be a dots. If you have more than 2 terms, and you can't somehow make it 2 terms, there's no ways it can be a dot. So the only time you're allowed to factorize it to be a dots is when your expression somehow is 2 terms. Now what do they mean when they say difference of 2 squares? When we say square, we mean a perfect square. Well, that doesn't say perfect, so let me erase. We mean perfect square. So what is a perfect square again? A perfect square is a number or a variable that can square root to a neat, nice, natural number. So let me give you examples of numbers that are perfect squares. 1 is a perfect square because it's 1 times 1. 4 is a perfect square because it's 2 times 2. 9 is a perfect square because it's 3 times 3. 16 is 4 times 4. 25 is 5 times 5. 36, and as you'll know, they go on forever and ever and ever and ever and ever. If you want perfect squares with variables, x squared is a perfect square because it's x times x. X to the power of 4 is a perfect square because it's x squared times x squared. X to the power of 6 is a perfect square because it's x cubed times x cubed. So what you start realizing is that any even exponent variable lands up being a perfect square. Numbers are a little bit more tricky because not all numbers are perfect square, but with exponents it's a lot easier. All even exponents can easily be divided into 2 identical groups, and so they're all perfect squares. So in every single question we're going to say to ourselves, is there a highest common factor? Once we've checked that, we're going to say, do we have a dots? And when we're looking for a dots, we're looking for a subtraction sign, we're looking for 2 terms, and both those terms have to be perfect squares. That's when we can say, yes, it's a dot. So it's almost like a 3-point check system. Okay, now in order for us to understand what dots are and how to factorize them, we need to know how to multiply out. The whole of factorizing, because it's undoing multiplying out, if you understand multiplying out very well, then you become very good at factorizing. So what I want you to remember, from products, I think you would have remembered this. This is a binomial times a binomial, so this is x squared, and then minus 2x. And I hope you notice that these brackets are almost identical. Plus 2x minus 4. Now I say they're almost identical because they're not absolutely identical, because they're the same terms, but they have different signs in the bracket. Now what happens is, when you have different signs in the bracket, you will hopefully remember this from products, these 2 middle terms always ended up cancelling. If the brackets were identical, but with different signs, our middle terms ended up disappearing. And why were they identical? Well, let's have a look at where they came from. These terms land up being identical because my first thing I do, x times the 2, which is 2x, granted it's minus 2x. And then these two, you're doing exactly the same product because these brackets are identical. And so I get minus 2x and then plus 2x, which means they disappear. And I'm simply left with x squared minus 4. So hopefully you remember that pattern from products. We did it in an exercise where we were like, oh my word, isn't this interesting? If the brackets are identical but different signs, the middle terms cancel. Now, we were saying those words then because we wanted to preempt this idea. Now, this answer is what we call a dots because it's a difference and there's two terms and both of those terms are perfect squares. So let's look at our next example, which is the same thing. These are identical brackets, but one's a minus and one's a plus. Now, notice here we had our plus first and then our minus, and now we have our minus and our plus. So my question is, does it matter which bracket is first? Let's have a look. X times x, which is x squared, that's a perfect square. Then x times positive 3 is positive 3x. Then I'm minusing 3x. Look, they're identical but with opposite signs. And then minus 9. A couple of things to notice. Do you notice that this is a minus? And this is a minus. And that in a difference of two squares, your last term will always be, it'll always be a subtraction between these two, simply because you're multiplying together opposite signs always. And so that's why it's always a difference of two squares, and we would never find a plus sign that to work like this. So what happens? My middle terms cancel, and I have minus 9, and that is now a dots. It's a difference of two terms that are both perfect squares. Now, if we can see how it multiplies out, we can see how to go backwards. So let's just look at the pattern again. We have identical brackets, but our brackets have different signs. Does the order matter in which you write it? The answer is no. You can put the plus bracket first or the minus bracket first. It doesn't matter. Now, I do a specific way, and in the next lesson, I'll show you why I do that way. So let's have a look at our summary here of what hopefully we've noticed. If you have a squared minus b squared, so if I give you one of these answers and I'm trying to go back to the question, that's called factorizing. And a squared minus b squared factorizes to a binomial times a binomial. And if it's a squared, that would have come from a times a. And if it's b squared, it would have come from b times b. So they're identical, except one has to be a plus and one has to be a minus. Now, we could have said the minus bracket first and then the plus bracket. It doesn't matter. I prefer to use this one. And in our next lesson, I will show you why I prefer that one. There is a very valid mathematical reason why I prefer that, but the reality is they're the same thing. Remember that multiplication is commutative, so you can swap around these two brackets whenever you feel like. So just to say this again, this is a dots because there's two terms. It's a difference of two terms that are both perfect squares. And it factorizes to a binomial times a binomial, and you say to yourself, what multiplies by itself to give you a squared? A and a. What multiplies by itself to give you b squared? B and b. And one's a plus and one's a minus. So your brackets have to land up being identical, but with different signs. So I'm just going to write this here. A dots factorizes to identical brackets, but different signs. So that is kind of our note on dots. What does it mean? How do we recognize it? How does it factorize? So hopefully all of this you've got down on your page in your book as your notes. Now what we're going to do now is we're going to do a whole bunch of examples. I think there's like 10 of them. And as we go, we'll write notes on the side. So maybe do this in your workbook so you have some worked examples with some nice notes. And then I'm going to give you guys some classwork to do. So what's the first thing we always look for when you're factorizing? You always check for our highest common factor first. Always. So if I look at this, there's two terms here. I don't see a highest common factor because one's x squared and one's 4. They don't have anything in common. So my second thing that I look for is I check, is this a dots? So I say to myself, is there a difference? Well, yes, because there's a minus. Are there two terms? Well, yes, there are two terms. Are they both perfect squares? Yes, they are. Now, if it's a dots, every dot comes from a binomial times a binomial. And we say to ourselves, and I'm going to just color coordinate this, we say what multiplies by itself to give me x squared. What multiplies by itself to get x squared. And that's what goes there. So this is x times x will give me x squared. Remember, it has to be multiplied by itself. These brackets have to be identical. Then we say to ourselves, what multiplies by itself to give me 4? What multiplies by itself to get 4? Now again, it has to be identical. So it's 2 multiplies by itself. Now our signs, one's a plus and one's a minus. Now why does one have to be a plus and one have to be a minus? There's 2 reasons why these signs have to be different. The first reason is, look at this last term. It's actually not 4, it's minus 4. So when you multiply these two together, you need to get minus 4. And the only way to get minus 4 is to have opposite signs. The second reason why these have to be opposite signs is your middle terms have to be opposite signs if they're going to cancel out. Because if you look there, there's 2 terms. Normally, a binomial times a binomial makes a trinomial, as in 3 terms. But if I scroll up here, all of these middle terms landed up with different signs, and so they disappeared, which is why you're only left with 2 terms. So those are 2 reasons why there must be a plus and a minus. Remember, the order doesn't matter, but I prefer the plus first. Okay, on to the next one. First thing you check for, is there a highest common factor? Nope, there isn't. Second thing you check for, is this a dots? Well, there's 2 terms, there's a difference, and they are both perfect squares. So a dots comes from a binomial times a binomial. We say to ourselves, what times itself gives you x squared? X times x. Great. Then we say to ourselves, what times itself gives you 1? 1 times 1. What are my signs? 1 has to be a plus sign, 1 has to be a minus sign. So yes, indeed, this was a dots. Remember to always check your highest common factor first. Cool, now once you get this type of pattern, it really is just a pattern, so it actually becomes quite nice. So question C, do we have a highest common factor? Well, we have 2 terms, and the one term is 4x squared and minus 1. Nope, nothing, no highest common factor. So the second thing I look for is this a dots? Well, it is a difference. There are 2 terms, and I think they're both perfect squares, because if I try and use my color to color coordinate, what times itself will give me 4? It'll have to be 2 and 2. What times itself gives me x squared? X and x. Right, what times itself will give me 1? What's 1 times 1? Now, signs, one's a plus and one's a minus, simply so that the middle terms will cancel and that when you multiply your ones together, you actually get -1. Great, so going swimmingly. On to the next one. Check for our highest common factor first. Now, I don't think in any of these there's a highest common factor at the moment, but tomorrow's lesson we're going to do ones where we start combining these two. So that's why it's such an important thing. And I'm writing it down every time, even though it doesn't seem to be working, because we will be doing examples where there are highest common factors tomorrow. Now, this doesn't have a highest common factor again, so I said to myself, is there a dots? Well, there is a difference, and there are 2 terms, and they are both perfect squares. And so every dots comes from a binomial times a binomial. And how does it work? We say to ourselves, what times itself gives you 9p squared? Well, 3 times 3, and p times p. And then we say, what times itself will give you 1? We've done that before. It's 1 times 1. And then my signs, one's a plus and one's a minus. Now, you'll know if you're right, because you can just multiply that out and check. Or you can say to yourself, I know I'm meant to get identical brackets with different signs. Do they look identical? Do they have different signs? Okay, on to the next one. First thing we check for in question E is a highest common factor. So is there a highest common factor? Well, there's 2 terms, but I don't see anything common. So I check for the fact that, is this a dots? Okay, firstly, is there a difference? Whoa, there's no difference. This is a plus. Okay, now it's tempting to think that this is a difference of 2 squares because look, there's 2 terms. This is 9p squared, which is 3p times 3p. This is 1, which is 1 times 1. So yes, there are 2 terms and they're both perfect squares, but it's not a dots. And the moment it's a dot, not a dots, this, I should say, does not factorize as opposed to not factorize. So this does not factorize. There is no way to factorize this at all. So I just put that in there to show you. Obviously, maybe I'd put that in a test just so you would go, it does not factorize, but that seems a bit silly. But don't ever see a plus sign and go, oh gosh, yes, there's perfect squares everywhere. It doesn't mean it's a dot. You have to have a difference. Okay, now why do you have to have a difference? Let's just quickly look. If we wrote 3p and 1 and 3p and 1, that gives you 9p squared, that gives you 1. What's the problem? You need these ones to multiply to give you positive 1. So they either both need to be positive or they both need to be negative because you need to multiply together to give you positive 1. Now, why don't those work? Well, let's check. 3p times 3p, 9p squared. Great. 3p times 1, 3p. And then 3p times 1, 3p. 1 times 1, 1. Now, what do you notice? The moment your signs are not different, do your middle terms cancel? No. So you don't get 9p squared plus 1. You get 9p squared and the 1, but you also here get 6p. And if I multiply this out, there's going to be a middle term of minus 3p and minus 3p, so they don't cancel. So that's why, even though it's tempting, I'm going to erase all of this so we don't think that it's possible. It's not possible. Simply because your signs have to be different to make the middle terms disappear. And here the signs are not allowed to be different because of the plus 1. Right, moving on. Question F. Is there a highest common factor? Nope, there's not. Is this a dots? And I think it's a dots because I see 2 terms. I see a minus, which is always important, and they're both perfect squares. So let's go and factorize this quickly. What multiplies by itself to give you a squared? A times a, and b to the power of 4 would be b squared times b squared, and we have by now know that to get 1 is 1 times 1, and because this is a minus, I know that my signs can be different, so it's plus and minus. So on to G. Oh gosh, is there a highest common factor? Oh my word, there is. There are 2 terms here, but this is a highest common factor. These terms have a highest common factor of 2. So if I take out my 2, 2 times what will give me 8? 2 times 4, a squared, minus 2 times what will give me 2? 2 times 1. Now you multiply this to check. That'll be 8a squared minus 2, so that's great. Okay, now this is an added thing that we always have to check now, which is new to us. Once we've checked for our highest common factor, we now have to also check for a dots. Now that I've taken out that highest common factor, in the previous lessons that would just be the end of the question, but now we know something more. Once we've taken out the highest common factor, do we see a dots? Now if I look at this term here, that bracket, that looks like a dots because there are 2 terms inside the bracket. There's a difference and they're both perfect squares. So my 2 is still going to stay there, but this bracket is going to further factorize into a binomial times a binomial. So all I'm doing now is I'm taking this entire bracket and factorizing it into a dots. So I say to myself, I have 4a squared. What multiplies to give me 4? 2 times 2. A times a has to be identical. What multiplied by itself to give me 1? That would be 1 and 1 to give me 1. And my signs, like we've always been doing, 1 has to be a plus and 1 has to be a minus. So that's a new type of thing for us. Once we've checked for a dots, that's no longer the end. We now must check, oh gosh, do I now have a highest Sorry, let me start that again. Once we've first checked for do I have a highest common factor, that used to be the end. Now we have to go forth and check is there a dots as well. So let's have a look at H. H, is there a highest common factor? Oh my word, what a shock, there is. This is 2 terms and I think 2 is common. Now 2 times 9 will give me 18, so it's 9x squared minus 1. Now in the previous exercises that would be the end, but now we have to check, do we now have a dots? And I think I do have a dots, because this is two terms difference, and they're both perfect squares. So I said to myself, what multiplied by itself gives me 9x squared? 3x times 3x. What multiplied by itself gives me 1, 1, and 1. And then as per usual, 1's a plus and 1's a minus. So this entire bracket factorized to all of that because it's a dots. Right, last 2 ones before you guys go and have a bash at this. Is there a highest common factor? Well, there's 2 terms, and the numbers are 4 and 9. Well, there's nothing that goes into 4 into 9, and there's x squared and then y to the power 4. No, I don't see a highest common factor at all. So I next say to myself, is there a dots? Well, there is a difference, because I see a minus sign. There are 2 terms, and guess what? They're both perfect squares. So this didn't have a highest common factor, but it does have a dots. Let's go have a look. What multiplied by itself? That would be 2x times 2x. Then what multiplied by itself would be 3y squared. And 3y squared, because you have y to the power of 4, and I have to divide it into 2 even parts. 1's a plus, 1's a minus. So that one was, I kept that one near the end simply because it was a little bit more complicated, because both terms were a little bit more complicated perfect squares. But it's not too bad. Okay, and our last one, is there a highest common factor? Well, there's 2 terms, and one's x squared and one's 1. So that's nothing highest common factor. So is there a dots? Well, let's check. Is this a difference? Yes. Are there 2 terms? Yes. Are they both perfect squares? Yes, they are. It's just that this one looks a little bit weird, because instead of saying x squared minus 1, it says 1 minus x squared. No problem. What multiplied by itself gives you 1? 1 times 1. What multiplied by itself gives you x squared, x times x, and then as we have been doing, 1's a plus and 1's a minus. So that looks a little bit different because we're used to x squared minus 1. There's nothing wrong with it being the other way around. Okay, dots are meant to be the really nice part of factorizing. So let's just quickly recap. How do you know it's a dots? Because you check for the difference, you check for 2 terms, and you check for them being perfect squares. Then every dots factorizes to a binomial times a binomial, and they're exactly the same except you have a plus and a minus. And you always say to yourself, what times itself will give you the first term, what times itself will give you the second term. Don't forget to always check for a highest common factor first, and then check for a dots in all questions from now on. Okay, so hopefully that made sense. Hopefully you've got down all the notes into your book and all of these examples, so you have worked out examples. So for the rest of the lesson, we are doing exercise 18.5, numbers 1 to 16. I have made a memo, so you can just look at the memo. Make sure that if you look at the memo and you understand where you went wrong, that you write yourself a little note and a correction. If you don't understand where you went wrong, or you'd like an explanation, just send me a message and I'll reply to you. Okay, well done.